Section: Introduction. In this section, we delve into the concept of instruction pre-training, which is a method we propose to explore supervised learning for pre-training. Instead of directly pre-training on raw text data, we enhance each piece of text from the raw data with a set of instruction response pairs generated by an instruction synthesizer. These pairs are created based on the content of extensive raw data, ensuring broad coverage and accuracy of knowledge. By developing the instruction synthesizer using open-source models, we can efficiently scale up the synthesis of diverse instruction response pairs across various task categories. To build the instruction synthesizer, we convert a wide array of existing datasets into the required format, where each dataset includes instruction response pairs and raw text that these pairs are based on. By fine-tuning a language model on this data, we enable the synthesizer to generate instruction response pairs for pre-training corpora effectively. Our approach differs from previous methods that rely on large or closed-source models, as we opt for cost-effective open-source models with 7B parameters. Through our experiments, we demonstrate the effectiveness of instruction pre-training in both general pre-training from scratch and domain-adaptive continual pre-training. In general pre-training, our 500M model outperforms A1B model in terms of performance, showcasing the benefits of instruction pre-training. Moreover, continual pre-training with instruction pre-training consistently enhances the performance of Llama 3 to 8B in finance and biomedicine domains, making it comparable to or even better than Llama 3 to 70B. Our contributions include proposing instruction pre-training for supervised pre-training, developing a scalable instruction synthesizer for generating diverse instruction response pairs, and conducting a thorough analysis of the synthesizer and synthetic data to understand the key factors behind the success of our approach. Section Summary. In this section, we introduce instruction pre-training as a method to explore supervised learning for pre-training language models. Instead of directly pre-training on raw corpora, we augment each text with instruction response pairs generated by an instruction synthesizer, enhancing task generalization and scalability. By fine-tuning the synthesizer on diverse datasets, we efficiently generate high-quality instruction response pairs, leading to improved performance in GEAL pre-training and domain-adaptive continual pre-training. Section: Inference. In this section, we conduct multi-round inference to generate few-shot examples. In each round, we add the texts and instruction response pairs from previous rounds to the current text. This helps the instruction synthesizer create new instruction response pairs based on the previous ones. For LM pre-training, after collecting the synthesized instruction response pairs, we use templates to diversify instruction formats and concatenate each raw text with its instruction response pairs. By combining the texts and instruction pairs from multiple rounds, we create an example for pre-training. We keep the pre-training settings the same as vanilla pre-training, training with the next token prediction objective and computing loss on all tokens. We test both general pre-training from scratch and domain-adaptive continued pre-training to see their effectiveness in different scenarios. In general pre-training from scratch, due to the large data requirement, we only convert part of the raw corpora into instruction-augmented corpora and mix them with fine-tuning data to enhance task diversity. For domain-adaptive continual pre-training, since less data is needed, we convert all raw corpora into instruction-augmented corpora and mix them with general instructions to benefit from improved prompting ability. We exclude the fine-tuning data from the general instructions collection. Our synthesizer is fine-tuned from Mistral 7BV0.1. A model with 7B parameters, which is cost-effective compared to larger models. During inference, about 5 instruction response pairs are created per raw text, each containing around 52 tokens. For pre-training corpora, we sample a subset of the refined web dataset for raw pre-training corpora, consisting of 200M pieces of text with about 100B tokens. We conduct 2 rounds of instruction synthesis to convert part of the raw corpora into instruction-augmented texts. We then mix in fine-tuning data for the instruction synthesizer to increase its sample ratio throughout pre-training. We implement models with different parameters using the architecture and tokenizer of Mistral. To enhance training efficiency, we use memory-efficient attention of X-formers. Detailed hyperparameters and evaluation settings are provided in the appendix. We use raw corpora from 2 domains: PubMed abstracts for biomedicine and financial news for finance. After 3 rounds of inference, we mix the instruction-augmented corpora with general instructions. We continue to pre-train Llama 3 to 8B on each domain and evaluate the models on domain-specific tasks. In the evaluation of pre-trained models, we compare the performance of models after pre-training. By incorporating fine-tuning data and transforming raw corpora into instruction-augmented corpora, we observe improved model performance on various benchmarks. Our method shows effectiveness in enhancing model generalization, even on unseen datasets. Our models demonstrate data efficiency across different scales compared to other open-source models. Section Summary. In this section, we conduct multi-round inference to generate few-shot examples by prepending texts and instruction response pairs from previous rounds to the current text. This approach enables the instruction synthesizer to create new instruction response pairs based on the accumulated information. We explore both general pre-training from scratch and domain-adaptive continual pre-training, showcasing the effectiveness of our method in enhancing model generalization across different scales and domains. Section: Instruction-tuned models. In this section, we examine the performance of our models during instruction tuning from pre-trained models. We notice that the model pre-trained with instruction pre-training surpasses the one pre-trained with vanilla pre-training, showing a steady improvement throughout the instruction tuning process. This suggests that aligning the training tasks during instruction pre-training and tuning stages helps the model transition smoothly between pre-training and fine-tuning, leading to faster learning on downstream tasks. Therefore, instruction pre-training seems to be a promising approach to reduce the need for extensive fine-tuning steps. Our main results, as depicted in the table, reveal that instruction pre-training consistently outperforms vanilla pre-training across most domain-specific tasks. Continuous pre-training with instruction pre-training significantly boosts the domain-specific performance of Llama 3 to 8B, even matching or surpassing Llama 3 to 70B. However, on the Finance NER benchmark, where instruction pre-training falls short compared to vanilla pre-training, we observe some variability, suggesting that this benchmark may not be entirely reliable. When we look at the ablation results for our pre-training data in the table, we see that removing the domain-specific instruction-augmented corpora leads to a decrease in domain-specific performance due to the loss of domain-specific knowledge. Additionally, constructing instruction-augmented corpora using rule-based methods limits diversity, affecting performance. Limiting synthesis to one turn instead of multi-turn synthesis results in instruction-augmented corpora with only one-shot examples, leading to decreased prompting performance. We then delve into the analysis of the instruction synthesizer and the instruction-augmented corpora to understand their impact on LM pre-training. Our goal is to develop a versatile synthesizer capable of generating instruction response pairs for any raw text. We evaluate its performance on both seen and unseen datasets, where the unseen datasets include various specific instruction formats. By assessing response accuracy and instruction response pair quality, we demonstrate the effectiveness of our fine-tuned synthesizer in outperforming the base model across different settings. Furthermore, we conduct experiments using an LM to evaluate the impact of synthesized instruction response pairs on helping LMs generalize to unseen tasks. By comparing the LM's performance with and without the synthesized pairs in the prompt, we show that our synthesized tasks consistently enhance the LM's performance, surpassing all baselines on both seen and unseen datasets. This highlights the effectiveness of our synthesized tasks in improving the LM's ability to tackle a wide range of tasks. Section Summary. In this section, we observe that instruction pre-training outperforms vanilla pre-training in few-shot performance on MMLU during instruction tuning, showcasing a stable increasing trend throughout the process. The alignment of training tasks during instruction pre-training and tuning stages enables rapid learning on downstream tasks, offering a promising solution to reduce the number of fine-tuning steps needed. Additionally, instruction pre-training consistently outperforms vanilla pre-training on domain-specific tasks, enhancing the performance of Llama 3 to 8B and even surpassing Llama 3 to 70B in some cases, highlighting the effectiveness of this approach in improving model performance. Section: Instruction Augmented Corpora. In this section, we examine the instruction augmented pre-training corpora by looking at context relevance, response accuracy, and task diversity. We randomly select 500 instruction augmented texts from the corpora and use GPT-4 to assess the instruction response pairs created. We ask GPT-4 to determine if the instruction matches the context of the original text, context relevance, and if the response is accurate based on the instruction and context, response accuracy. Additionally, we task GPT-4 with categorizing each instruction response pair into different task categories. Our instruction synthesizer generates pairs covering 49 task categories, with over 85% relevance to the context and 70% response accuracy. We group these task categories into 9 main task scenarios, showing the variety of tasks generated. The distribution of these task scenarios in the instruction augmented corpora for overall pre-training is illustrated in a figure. Our synthesized tasks span all task scenarios, indicating the effectiveness of our instruction synthesizer in creating diverse tasks. Regarding synthetic instruction generation, previous studies have focused on post-training, while our emphasis is on pre-training, making our work complementary to existing research. Our experiments reveal that pre-trained models benefit more from post-training with instructions, emphasizing their complementary nature. Our method differs from related works in several aspects. Firstly, we concentrate on learning directly from raw corpora instead of distilling knowledge from strong models. Secondly, our approach can be applied to various tasks, unlike more task-specific methods that rely on a few specific examples. We also surpass rule-based methods by enhancing instruction diversity. Furthermore, we plan to explore how iterative techniques used in other studies can complement our method in future research. When it comes to data curation for LM pre-training, the process typically involves collecting, cleaning, and organizing data. Most pre-training data are gathered from the internet to ensure diversity. However, web-scraped data often contain low-quality and duplicate content, requiring data cleaning techniques such as language identification, perplexity-based filtering, classifier-based filtering, and rule-based filtering. Data organization involves fine-tuning the data, including selecting relevant data and creating training instances for downstream applications. Our work takes a different approach by enriching raw corpora with large-scale supervised signals, exploring a new direction in data curation for pre-training.